Hey everyone, Johnny here and welcome to this video. Today we're going to be looking at optimization problems using differentiation. So questions which require you to find the maximum or the minimum of a particular thing. We're going to be looking at that process using this example here, but I'm going to be applying principles which is represented by the acronym DERDSTER. Okay, so if you want to be a nerd or a nerdster, this is the best I could come up with. If you want to be a nerdster at optimization problems, then you need to be a DERDSTER, or you need to use DERDSTER. Okay, so we're going to use that acronym, we're going to use these principles that will apply to any type of optimization problem. So even though I'm looking at a particular category of an optimization problem here, I'm looking at one that involves shapes. You won't always get a question that involves shapes. Even though I'm doing that here, the process, the steps that I'm going to use can be applied to any type of optimization problem. Okay, so let's have a go at this and I will walk you through what all of this means, what DERDSTER is, and how you can use it by doing it to this question. So let's imagine that the question wants you to find, or rather gives you, a cylinder with radius r and height h, and it's placed inside a cone. So you have a cylinder inside a cone with a radius of 6 centimeters and a height of 20 centimeters. Find the value of r, the radius of the cylinder that is, that will maximize the volume of the cylinder. Okay, so what's the first thing that DERDSTER tells us to do? It just says, draw a diagram, do a diagram that represents this information, and also try and fill in the diagram as much as you can using that information. Okay, so not just the direct numbers provided, but any other kind of expressions or details on the diagram that could be relevant potentially. Okay, so let's do a big diagram here. First thing, I need to do a cylinder inside a cone. So I should probably draw a bigger cone first. Let's do that. I'm going to get a better texter to do this for you. Okay, so we're going to draw a big cone. And we can kind of represent the cone like this. Not a perfect diagram here, but that will do. That's our cone. And then we need to actually do a cylinder inside that cone. Okay, now here's the thing, and this is the nature of the problem, and this is why you're doing this. I could draw a million different types of cylinders. I could do a really thin cylinder, if you can see here. I could do a really thin cylinder like this, see? I could draw it and then do it very long down. Okay, as long as it hits the edges there, I could draw it all the way down there. Or I could do a very thick cylinder. I could start drawing it around here and make it go down to the bottom, so it wouldn't even go up there. The question is, which cylinder, which dimensions must the cylinder have to have the biggest possible volume? The very thin cylinder up there that starts at the top and goes all the way down through the middle is probably not going to have the biggest volume. And that's actually what the question wants us to find. Find the value of the radius for the cylinder, right? So that's the width of the top of the cylinder and the bottom. That will actually give the biggest volume inside this cone. So I'm just going to draw a cylinder roughly in between here. We don't know, of course, exactly how wide this cylinder should be. But hopefully you see the point here that we're trying to find what type of cylinder, whether it's a really thin one or a really thick one or right in the middle here, that will actually have the biggest volume. Because they won't all have the same volume depending on how you draw them. What we now need to do is use these numbers here. It says that the cylinder has a radius r, so I'm going to do a dot here. The radius goes from the center, so that's r. And it says it has a height of h, so that goes straight down here. We can call that h. We can also call this h. We can also call this h. Because all of those lengths there, all of those lines there, the line through the middle of the cylinder and the two there, all have the same height. They're all parallel to one another. This is what I mean by fill in as much as you can, because you don't know which value might be relevant to you when you're doing your working out. Okay, so by the same token, we could put in r here as well. So put in r at the top, put in r at the bottom. Good. What else can we fill in? Well, we know that it has the actual cone has a radius of 6. Now, because it has a radius of 6, and I don't want to go through the r here, I'm just going to do it below. So the cone itself has a radius of 6, so that's to that center. And it has a height of 20. Okay, so there's the cone's dimensions, there's the cylinder's dimensions. We'll see what else we can do with that diagram in a moment. the next thing we actually want to do, and this will help us fill in the diagram more, is write in the equation. Now, I've done my diagram, right? I might fill that out a bit more when I know where I want to go with this, but I want to now write the equation or the formula for the thing I'm trying to maximize or minimize, okay? In this case, maximize. Find the value of R that will maximize the volume of the cylinder. So what's the actual equation or formula that's relevant here? It's the volume of the cylinder. So what is the volume of a cylinder? Well, the volume of a cylinder, and hopefully you just know this, or you can use a formula sheet, but I would definitely memorize the basic, shapes and the volumes and surface areas of those shapes. V equals pi r squared times h. Okay, so it's pi r squared h is the volume of a cylinder, not a cone. I don't need the volume of a cone here. So I'm trying to maximize the volume of a cylinder. So that's the volume. That's the equation that you want to write down following Durdster. Okay, so we've now done that equation. Check. Now we need to replace the value of the pronumeral that we don't need to satisfy this question. So what I mean by that is, see how it says find the value of R? Find the radius that will maximize the volume of the cylinder? It doesn't say find the value of h or the height that will maximize it. That means I want to replace h with an expression for R. I don't want to get rid of the R because the R is the thing I need to actually find, the thing I need to actually solve for to give the maximum volume. So I actually want to get rid of h and replace it with a value for R. Okay, so the question is, how do you actually do that? You've got one equation here which has R and H, and you could try and reshuffle this and rephrase it so that you had an expression for H in terms of everything else, but that wouldn't be useful. You want to leave this equation alone, and you need to get another bit of information. This is the crucial thing. Once you have this formula or equation that you're going to use to maximize or minimize, you need to find another expression, a second expression or equation or formula or something that will allow you to get H in terms of R. Okay, so I want to find a relationship between H and R that isn't this relationship. How are we going to do that? We have to look back at our diagram to do this replace step. Okay, this is the hardest part of any max-min problem. This is the hardest part. It's to find what should go there. What should replace H? We need something that is still the same as the height, but doesn't actually have the letter H in it. We want to have the letter R in it because that's the thing we are going to differentiate. Okay, so what can we do with our diagram here? What can we fill in that we haven't filled in yet? Well, if you look carefully, we know that this radius here is 6, and the smaller radius here is R. So that means you technically could find the radius of this part in between, or this part on the outside. Okay, so even though this smaller part is R, that means that this part here is 6. It's the big radius minus the small radius. This is the really important part to figure out. And the more you practice these and the more types of questions you look at, the easier this will get. So you can see that I can fill in that this smaller side here, which is the leftover part of these two radiuses, is just going to be the big radius 6 minus the small radius. The same logic applies with the height. So see how the big height is 20, but the cylinder height, the smaller height, is h? That means that the leftover height, so the height between the top of the cylinder and the top of the cone, must be the big height minus the small height, which is 20 minus h. Great. So you have 20 minus h for that and 6 minus r for that. What else can you see in this diagram? What I can also see, and again, something that you'll see more and more easily through doing practice, is that actually if we follow this line down, if we follow that line down there, you can actually see a right-angled triangle emerge at the top. See the cross-section there? You can see a right-angled triangle on the edge there. And that right-angled triangle, which is just from there, the bottom of it is R, as you can see. That's just the radius of the cylinder. I'm just extracting this out. And the height here is 20 minus h. You'll see why this is relevant in a second. And then what you can notice is that down here, you have another right-angled triangle. you have the triangle in this part. So if I extract that out, this bigger triangle, it's a right angle triangle as well, because obviously that height comes straight down perpendicular to the base. And the bottom here is 6 minus r, and the side here is h. So you have two right angle triangles. And the key thing you want to know for this type of question is that those two triangles, those two right angle triangles, are similar triangles. So that's the key insight for this type of question. You have similar triangles. And a triangle that is similar to another one doesn't mean it's the same. It's not congruent. It's not a congruent triangle, but it is a triangle that has the same ratio of sides. So, for instance, if this triangle is bigger than this triangle and they're similar, okay, it just means that whatever this side is divided by this matching side in the other triangle, that ratio is the same as this triangle proportionate to this side, this side of this triangle proportionate to this side. So let's say that you have two triangles which are similar, but one triangle is double the size of the other. It just means that if you were to look at one side of the smaller triangle, you would need to double that side to get to the equivalent of the other triangle. And then you would double all of the other sides of that smaller triangle to get to the bigger triangle. So there's a consistent number that you would multiply the smaller sides by to get to the bigger sides. And the reason that is because they're similar triangles, and that means they have the same angles. They don't have the same sides necessarily. They would be called congruent triangles, the same triangles. They just have the same angles and are in the same ratio. The sides are in the same ratio. So that's the key trick with this question. See how important filling out the diagram is. Okay, so fill in the diagram with those extra right angle triangles that you can take away from the information that the question directly gave you. And now you have a similar triangle relationship. What can we do with that? Why is that important? Remember, we're trying to replace h with r. And to do that, we need some other equation that can help us get h in terms of r. Well, when you have similar triangles, and you just need to know about how similar triangles work, what happens is, as I said, the sides that are matching, so for instance, the side on the left here, and then this side on the left here, they should be in the same ratio as the bottom side divided by the other bottom side. Okay, so there should be a consistent ratio. They're in proportion. So we can actually write that out here. So we have, let's start with this triangle up here, or we can start with this triangle here. So see this side length here, h? See how this is h? We can write h. I'll just get another text here. We can write h divided by, the other equivalent side, which is 20 minus h. Okay, so we have h divided by 20 minus h, because they are both the left sides of these two similar triangles. I should also note that the reason they are similar, which I should have made clearer, is that they both have a right angle. And because these two sides here, if you look at the bases, look at the bottom here and this bit here, because those parts are parallel, it means that this angle is the same as this angle, because they're called corresponding angles. They are corresponding angles on parallel lines. Do you see how this angle, represented by this, is the same as this angle, represented by this? Because if I was to extend these lines, they would be parallel. And we know that when you have parallel lines and you have this F shape of angles between them, they are the same. So these are called corresponding angles on parallel lines. Okay, you've got to have parallel lines to actually get that. And then because those corresponding angles are equal, and because they both have a right angle, that means that the third angle that they both have must be equal as well, because all angles equal 180 in a triangle. So because two angles of each of those triangles are the same, that means that they are similar triangles and that all angles would be the same. So all sides are therefore in the same ratio. Okay, I hope that makes sense. Have a look at any videos we have on similar triangles for more on that. But we are now writing the sides in ratio. Okay, so h, this left side, divided by that other left side, 20 minus h, should be the same as 6 minus r. We have to be consistent here. If you're going to start with this triangle for this one, you have to start with the same triangle for the other side. So 6 minus r divided by r. The reason why we divide those two, because they're both the bottom sides that you see there. Okay, so similar triangles means that these should be in the same ratio. Now we have an equation. Now I want to get h by itself. I can see that there's an h on the top and the bottom, so I want to just start solving this and getting rid of the denominator. That's always what you want to do here. Get rid of the denominator. So multiply, you can cross multiply. I can multiply the h by the r to get rid of that, and then I can multiply, and I should put brackets here because these have two terms, I can multiply this numerator by this denominator, and that gets rid of the denominator. So that's called cross multiplying. So h times r, we get hr equals 6 minus r times 20 minus h. Okay, so hr equals 6 minus r, 20 minus h. You can see I've just cross multiplied up there. That gets rid of the denominator. Now we want to expand those brackets. Expand those brackets. 6 times 20, 120. So I'm just doing this, going fishing, as they say. 6 times 20 is 20. 6 times minus h is negative 6h. Negative r times 20 is minus 20r. And negative r times minus h, or negative h, is positive rh. We now want to solve that. We now want to simplify that. So because we have h on both sides, so we need to collect like terms. Okay, so I'm going to move all of the h terms on the right side over to the left side. So let me pull those over. To pull them over, obviously you need to do the opposite of what's happening. So because it says 120 minus 6h, I need to plus 6h to both sides for it to be even. Okay, so that gets rid of that from that side, carries it there. To get rid of plus rh, I need to minus rh because that would give 0 there. But what I do to one side, I have to do to the other side. So minus rh. Okay, now rewriting all of this, I'm going to get hr plus 6h minus rh equals 120 minus 20r. Now you can see here, hr minus rh, well, r times h is the same as h times r. So it's actually the same as hr, which means we have hr minus hr, so they will cancel each other out, which means you are just left with 6h equals 120 minus 20r. So I'll rewrite that up here. So we have 6h equals 120 minus 20r. And what we now have is we can divide by 6 to get the h by itself. So we have to divide all the terms by 6, and that leaves us with h equals 20 minus, and then 20 over 6 can be simplified to 10 over 3 because 2 goes into both the top and the bottom there. 10r over 3. Voila, you now have an expression for h in terms of r. And because this is a true statement based on the information in this diagram, because we use similar triangles there, we now can rewrite the volume. That was the hardest part of this question. So we now rewrite this volume not as pi r squared h, but as pi r squared bracket, and wherever the h is, we put in this 20 minus 10r over 3. Now we have volume expressed just in terms of r. Remember that pi is not actually an unknown. Pi is just a number, 3.14, whatever. We just use that for convenience. Okay, so there's only one letter there we don't know, which is the r, which is great because that means you can now go to the next step and differentiate this expression. We want to find the first derivative of the volume so that we can maximize or minimize it. Because when you differentiate something and find the first derivative, you are then allowed to find what the gradient is at different points on it. Okay, so if we were talking about a graph and you found the first derivative, excuse me, you would then be finding the slope at different points, and we want to know when it's a maximum or a minimum, so we want to know when that gradient is 0. Okay, so the first thing is to find the first derivative, because the first derivative allows you to find the gradient at different points, and we want to then find when the gradient is 0, because that would give us either the maximum or minimum value. Okay, and we'll test that in the step after. So let's go from here and find the first derivative. So the first derivative here, well, before we do that, actually, we should expand the brackets because that's going to make it a lot easier. So we're still just doing the normal volume expression. 20 pi r squared minus 10 pi r squared, or 10 pi r cubed, I should say, because it's r squared times r, 10 pi r cubed over 3. Okay, so the over 3 carries there. Perfect. There's our better expression for the volume. So that's not the first derivative yet. We're going to differentiate that now. Okay, so differentiate in that volume there. Have a look at what happens here. We get the first derivative. To do that, we get the 2 up there. Okay, remember there's an r squared there. We get the 2, we use the chain rule, so 2 times 20, or not the chain rule even, just the basic rule of differentiation, where the power will times the front. So we get 40 pi r, okay, because you have to subtract the power by 1, that's the rule, after you multiply that power by the number at the front. So you get 40 pi r. Let's do the same here, minus, now 3 times 10 is 30 pi r squared, because we subtract 1 from the 3, over 3, and we can then simplify that, because we've got 30 over 3 as 10, because 3 goes into 3 once, 3 goes into 30 3 times. So now we have 40 pi r minus 10 pi r squared. What we should now do before we make it equal to 0, before we solve for the first derivative equaling 0, right, in Dördster, we should actually factorize this now, so we can take out 10 pi r as a common factor. So let's take out 10 pi r. We're left with 4 minus r. Perfect. And now what we want to do is, because we've differentiated, because we found the first derivative, we want to solve for y dash equals 0. Again, the reason we're making it equals 0 is because that allows you to find a maximum or a minimum. Imagine it as a graph. That's that top point or the bottom point. So we make that equals 0. See how I've made the first derivative equals 0. And then we keep this expression here, because we're now going to find which value of r would make this side equal to 0 and satisfy the equation. So which value for r would we need to sub in to get this side, this whole right side, equaling 0, the left side? Well, you can see, first of all, we can just divide off 10 pi. Just divide off the number at the front there. It's multiplying everything. Okay, remember that 10 pi r is over everything, so we can just... We don't want to get rid of the r, just the 10 pi, okay? Never divide off by the r, because that's the thing we're trying to solve for. Just get rid of the numbers out the front. So 0 equals r, 4 minus r. And then what you get there is an interesting situation where there's 2 possible answers. I could replace r, and this is what you do whenever you see the pronumeral at the front of the bracket multiplying by it, right? You could actually make r equal 0. It's called the null factor, but you don't need to remember that. Just know that if I made r equal 0, think about it, it doesn't matter what's inside that bracket. 0 times anything in the bracket will make the whole thing equal 0, which will therefore satisfy the equation. But that's not a viable answer. Even though that mathematically here is an answer, it's not an answer for this question, because imagine if you made the radius equal 0. You wouldn't even have a shape at all. You can't have a side length that is negative or 0. Okay, the side length has to be positive, or there is no length at all. There is no side, unless it has some length. So a radius of 0 doesn't make sense in the context of this question, which is based on shapes, okay, which need to have a positive length. So that doesn't make sense. What's the other solution? Well, I can look inside the bracket and say, look, 4 minus r, I need 4 minus r to equal 0. If I made r equal 4, or I can just solve the equation, I can just plus r to the other side here. If I make r equal 4, that is going to make the bracket equal 0, therefore the whole side will equal 0. Okay, it doesn't matter that it's 4 times, because 4 times 0 is going to equal 0. So r equals 4 is our answer. That will give us, hopefully, the maximum volume of the cylinder. But we don't know that for a fact yet, because even though we've now solved it, we've got r equals 4, we need to test it to make sure it gives us a maximum and not a minimum, because sometimes you could get 2 possible answers, and one of them gives you the minimum volume and one gives the max volume. Okay, so here we're trying to find the max. To test it, we either need to use the second derivative or a table of values, okay, which you can look at in another video on how to use those. But in terms of the second derivative, which I'll use here because the first derivative wasn't too complex, If the first derivative was something really complicated, I wouldn't use the second derivative to do this test. I would use a table of values using the first derivative. But here's basically what you can do. Okay, so using the second derivative, I'm going to first of all get the first derivative and to get me to the second derivative. So remember, the first derivative was this here. So I'm now going to get the second derivative, which is 40 pi r. It's just 40 pi because it's the number in front of the r. Minus, now again, because it's got a power, I times the power by the number at the front. So it's going to be minus 20. And then subtract 1 from the power, as always, and you're going to be left with r, just r to the 1, which we don't need to write the 1. From here, what we now want to do is, because I have now got the second derivative, I've got the second derivative using that first derivative. Okay, so this is the second derivative. I've just already differentiated that. Because I've got the second derivative, now what I do is I'm going to substitute r equals 4 to test it. I'm going to see what is happening to the second derivative. And you should know that the second derivative tests the concavity. We are now testing the concavity. Okay, and what does the concavity mean? It means, have a look at these points. It means the shape of the actual curve at that point. So is it concave up or concave down? What is the curvature? So have a look at the minimum here. If you have a minimum turning point, if you have found the minimum volume, then the concavity will be concave up. It will be positive. So just note that the concavity there will be positive. That is concave up. It's happy, right? Think about it. If something's up, if you're feeling up, you're feeling positive. So the concavity, the second derivative, when you sub in that value there, for instance, r equals 4, would come out as a positive number because it's concave up. There's a smiley face. See the shape, the curvature? It's curving up. Here at the maximum, it's curving down. It's a sad face. And because it's a sad face, it's negative, right? It's in a negative mood. The second derivative will be less than 0. Even though the first derivative is equal to 0, if it's a maximum turning point, because it's curving down, it's facing down, it is concave down. Okay, so the value should be negative. That's how we're going to prove if it's a maximum. If it's a maximum, it's got to have that characteristic. If it's a minimum, it would have that characteristic. Okay, so applying that here, we hope that it is therefore negative. Okay, so let's have a look. We sub in r equals 4. We get 40 pi minus 20 pi times 4, which is going to be 40 pi minus 80 pi, which is going to equal negative 40 pi. And you could put that in your calculator, but remember, pi is about 3.14, and that's clearly going to be a negative number then. Negative 40 times 3 is negative. So it is less than 0. That's how you say less than 0, right? At r equals 4. Therefore, concave down. Remember, if it's negative, you're feeling down. It means it's got this shape. And if it's got that shape, it means that the point you just found is at the top. It's a maximum. So it will give the maximum. And that answers the question because it's saying find the value of r. I'm now looking to see if I've answered the question. Last step. Find the value of r that will maximize the volume of the cylinder. Well, using that test, I have found the value of r. It is r equals 4, which will maximize the volume. The final thing you may have to do for a type of question, not for this particular question, but the final answer might actually be the volume itself. So pay careful attention to what the question actually asks for. If you need to give the maximum volume, then what you would then do, the kind of final step here, would be to substitute r equals 4 into the original, into V, into the original volume to get the max volume, okay, to give you the maximum volume. So let's have a look. We know that V from before, we want the expression that had r in it. We know that it equaled 20 pi r squared minus 10 pi r cubed over 3. So you can see I've just rewritten in the volume. And then what you would do is you would just substitute 4 there. And you would substitute 4 there. And once you actually figure that out, you can get to the final answer, which will be the final volume, okay? So that would give you the final volume if you then put in the r equals 4 back into the original volume. In this case, we didn't have to do that. Make sure you always read over the question at the very end when you think you're done to make sure you've answered what it actually wants and that you haven't fallen one step short. Alright guys, that is the end of the video. I hope that helps. If it did, please like the video. Make sure you subscribe to the channel for more content and click the bell so you are notified. I'll see you in the next one.